All right, line M1, learning task 1, we're going to take a look at alternator construction. Specifically, we're taking a look at three-phase alternators. We've talked very briefly about single-phase alternators in first year, as well as a little bit inside of second year. And then we have also talked about DC generators, which is different than an alternator. An alternator implies the fact that there's going to go and be alternation, meaning that we're going to go and have in the positive and we're going to go and have inside the negative direction itself. We're going to look at the three-phase ones, and we're going to go and classify them into two main types. The first type that we're going to talk about is going to be what's called referred to as the revolving armature. And in the revolving armature, we are going to go and have the stator, that's the stationary part over here, that is going to go and have my DC field. It's going to be stationary. I'm going to go and have my rotor, that's going to be the rotating part over here, that is going to go and have my actual three-phase output. That is going to go and get taken off of it. So what I'll do is I'll supply DC into these stator poles over here, and the stator poles are just going to, we're going to have one line in, it's going to go through this one, that's going to connect to the next one, go through this one, connect to the next one, go through this one, connect to the next one, go through this one, and then come back out. So we supply one line in, one line out, and what we'll get is we're going to go and get alternating north and south poles off of these ones. North, south, north, south. Like that we would have. Once we've got this north and this south, we would then go and have a bunch of lines of flux that are going to go through from norths to souths, and then norths to souths, like that. We'd set up these four lines of, or these four individual lines of flux over here, and then what we'll do is we're going to go and have our armature. This is the side view of the armature. This is the end view that we were looking at over here. The side view of our armature is going to look like this. We would just go and attach this thing to our prime mover. It's going to be inserted inside here, and we're just going to go and rotate it. As it rotates to those fields, we're going to go and generate AC voltage. The armature itself is going to have some multiple of 3 windings on there that are going to be equally spaced apart by 120 degrees, so that I'm going to be able to go and create those 120 degree sine waves. That 120 degrees of phase displacement comes from the fact that we always do have to place these things at some sort of a third type of split. Whether we got 3 windings or 6 windings, we can adjust our rotation. There's a bunch of other generator theory that are alternator theory that we're not going to go into, but we are able to go and build, more than 3 windings off a period of time. We could have ABC, ABC, ABC going around this thing, and we would just go and adjust our rate of speed to get that 60 hertz out. Irrespective of how we do it, we have to go and take the power from these 3 windings that we're going to have on here. I'm just going to go and draw this as if we have got an A winding over here. We're going to have to take the power from the A winding out, and so the A winding is going to go to a slip ring. My B winding is also going to have to go to a slip ring, and my C winding is also going to have to go to a slip ring. Now, all of these connections don't actually come flying out like that. They're all going to be done along a milled groove inside of the shaft of the alternator here, but they're going to make connection to those individual split rings. And then in most cases, when we're looking at a revolving armature, this connection inside here is going to be already pre-done. We're going to have the option that we can have this thing set up as a Y, or we could have it set up as a delta, and we're going to talk about those connections later on. But the big important thing to look at with the revolving armature is that we have to carry them out to these slip rings. A slip ring is nothing more than a continuous piece of metal. It's going to be a harder type of metal, usually some sort of a brass. It's going to be like a commutator type. And then up against that, we are going to go and have a brush that is going to be placed up against it. This is different than a commutator. Commutator switches. This maintains, because what we see is if I go draw the shaft of my alternator here, we're looking at this thing from the end. The shaft of my alternator is going to have a groove that's going to be along it. We're going to call that the keyway. But further on down inside here, inside of that keyway, we'll actually have our conductors that are going to come through, and they're going to attach on the inside of that slip ring. The slip ring itself is going to be mounted on a plastic or a ceramic type of base that is going to insulate it from the actual shaft itself. And then all that we do is, as we provide power along here, it's going to get picked up by this brush, which rides along the outside and carried to the outside. There is always an issue anytime that we're using brushes and slip rings or brushes and commutators, and that's always going to go and be the fact that we're going to go and have some arcing and a little bit of sparking. That is also going to go and happen off of these. In this case, it's going to limit the amount of current that we're going to be able to go and take out of this machine, because we just can't carry massive amounts of current through something that has arcing, sparking, and friction because we just generate too much heat. We have too many failures off of it. Over here, what they're showing us with these three little components is they're showing us that they've got these three brushes. Instead of mounting them all in a line, you know, here, here, and here, they've just mounted them around here so that you can access each of the brushes without having to tuck behind any other ones. They're going to be limited, these type of alternators, because of that whole slip rings of brushes. We're going to go and keep these things down to small values of voltage and small values of current. Too high of a voltage, we get too much arcing. Too high of a current, we get too much heat where it's going to go through those brushes. What we have much more commonly is we are going to go and have a revolving field type of alternator. And what happens inside of a revolving field type of alternator is we are going to go and have our windings that are going to be connected on the outside of our machine. So this is kind of just showing here that we have got a bunch of laminations over here, and then they're showing each of these as being a single connection. Okay, so this is my red line. This over here is going to be my black line. Now in reality, we would have many loops. This is going to be my blue that I'm going to go and have over here. Red, black, and blue, and then all we're going to do is rotate that magnet on the inside. We're going to create a rotating electromagnet that's going to be coupled to my prime mover, whatever's going to be driving this thing for the alternator. And as we go and drive that, this magnetic field is going to go and rotate. And so what we would see is that this magnetic field is going to go send lines of flux that are going to travel through from north to south. I'm going to redraw mine because they start to swoop them. I'm going to just draw it through straight like this. They're going to take the shortest path, which is going to be going directly into the alternator, or into the stator of the alternator, and then they're going to go and complete their magnetic circuit by coming back around and coming back in. So if I take a look at these lines of flux coming out and those lines of flux coming in, I see that they're coming out at 90 degrees to that pole face. We'll just draw these ones over here, doing the same thing. As these rotate around, so I don't know if I can grab this. Let's see. Sometimes this computer thing doesn't work out well. Other times it works out like a boss. As I grab this, what happens is that oh no, that does not work out well at all. 2 seconds, let's try and group it. Much more better. As I rotate my magnet on the inside of this thing, what you see happening, and I know that my little red and black and blue marks are moving there, but what you see happening, particularly up at the top one, I want you to examine this top one right over here. We're going to be looking at that guy. As we go and rotate this field around, what I see is that right now it's in parallel, and then right there where I've got lines of flux going through it, you can use your left hand generator rule, stick your first finger pointing toward the top of the page, that's the direction of flux, stick your thumb in the direction of thrust, that's going to be the direction of thrust on the conductor. So if the field is moving this way, it's like the conductor is moving the other way, so your conductor, your thumb is going to be facing off towards the left-hand side, and you would see that right as this passes through, we're going to have a current coming directly out of that towards us. And then we're going to have less current because we're not cutting at 90 degrees, and then we're going to go and move. We're still following this, the first one that we looked at. We see that then it cuts through the next one, that one's going to peak, and then it's going to cut through the next one, and that one's going to peak. And what we're going to see is we're going to see that we now get this AC peak, etc., run by our prime mover. It's a really handy thing for us because our field ultimately does not have to be all that large. Our field is, generally speaking, going to be a relatively small electrical draw. Now they show us a couple of small components inside here. This little symbol that they have is an electrical symbol that we would go and use for brushes. It implies the fact that there's a shaft and that there's something that is riding up against the side of that. This is going to be my brushes and slip rings. All I need to do for my revolving field type is I need to go and provide 2 slip rings, one for my DC in, one for my DC back out on this thing. We provide those 2 lines in and out of this thing. It creates this DC field, and then from that DC field and the prime mover, remember energy cannot be created nor destroyed, it can only change form. From our prime mover, so the diesel engine, the water turbine, whatever it is, we're going to convert that into electricity. Of our revolving field types of alternators, we've got two main types of revolving field alternators. We're going to go and have the salient pole, and we're going to go and have the cylindrical alternator. And they're really going to be selected based upon what we have for a prime mover. This, because it's much larger, means that we are going to go and have much more centrifugal force. So we are going to have to go and use a prime mover that is going to go and be slower, low RPMs for these ones. If we go too fast, we're going to go and have way too much centrifugal forces that will actually start to go and pull these windings off of their individual components. We're also going to go and use this because if I've got something that is rotating relatively slow at the very center, by the time I take it to an outside radius, that rotation is seen as being really, really fast, which also allows us to go pick up 4 values of frequency. What we have over here is I have got my, they say S rings over here. That's going to be my slip rings. My slip rings are going to go and be connected to each of my windings. I'll just highlight that inside of red here. This one's going to have one. And then this one over here is going to go through the shaft, but it's going to connect over to our other slip ring. Here's our 2 main slip rings that are going to be around that shaft. And then all we have is we're going to go from coil to coil to coil, down one and back up the other, down one, back up the other, down one, back up the other, with windings, obviously, as we're doing this. But what that's going to do is that's going to go and create these alternating norths and souths that we're going to go and have on each one of these. So I'm just going to go and have a north, south, etc. I place this whole assembly inside of my stator, my stationary part. Don't worry about the noises. Eli is just going nuts for some reason again right now. I don't know. For those of you who don't know, Eli is the cat that lives in the garage over here. But anyways, if you take a look at the stator itself, the stator is going to go and have my windings that are going to be placed around it. Now I'm going to have an even amount of windings. Whatever I've got for my rotor, I'm going to need to go and see the same types of windings on my stator. So however many of these I have, I'm going to have the same amount that are going to be on here, but it's going to be divided down by 3 because we're doing 3-phase. We have an A, B, C, etc. inside of here. An A, a B, and a C. That should span across one entire north to south section over there is what I should see across an equal type of size over there. So I'm going to go and take my main power off the stator over here at the bottom. You can see the main leads coming off of that thing. I know they're not in sequence right now, but that's all right. We are going to go and pull those things off the bottom over there, and we can carry massive amounts of current and voltage out of these because there is no brushes or commutator or arcing or sparking or anything like that. We rotate it inside of here. It's going to be relatively slow. The last thing that we have on here that we'll talk about later on is going to be a damper or amortisseur winding. I have no idea if I'm pronouncing that right or not, but it is going to go and dampen down fluctuations in our prime mover. It's not designed for electrical so much as it is for mechanical. It's going to give us some motoring effect in the opposite direction to go and counteract any sort of speed fluctuations that happen on our prime mover. Because we're going to use this with slow speed prime movers, 1800 RPM and lower, generally speaking. Things like engines, diesel units, things like water turbines, things like our wind turbines, anything like that that's going to be relatively slow is going to be run off of that. If I want to go to relatively high-speed operation, I'm going to have to go to a cylindrical rotor, and it's going to be a much longer and skinnier type of thing. And the reason we go longer and skinnier is because we have less centrifugal forces that are going to go and act upon my individual windings that are going to go and be inside of it. Same deal as before, we're going to have north and south inside of here, and we're going to go and have our 2 slip rings identified right over here, and we are going to go and have those fed just through milled shaft slots over here out to my north and south poles that are going to be inside here. The actual stator, they're showing us, this thing from the end is going to be relatively long and skinny as well. We use these inside of high-speed operations, particularly in steam turbines. And you might not be familiar with this steam turbine as an electrical generation. Over here in BC, almost all of our generation is going to go and be off of hydroelectric. And we're always going to be, well, not always, but almost always going to be using these ones here, the salient pole type of alternators to go and generate. In a lot of other areas of the country, it's flat, it's boring. They don't have mountains, they don't have a lot of the fun that we have out here, and so they don't have places where they can go and store water behind a dam and then run it down a mill race to create electricity. They either have to buy electricity or they have to go and generate. And so that's where Homer Simpson's power plant comes in. Everybody is familiar with The Simpsons. If you're not familiar with The Simpsons, I don't even know what to say at this point. So I'm not going to say anything. Instead, I'm just going to go and draw Homer Simpson's, power plant over there. You guys have seen these things. It's a terrible drawing. You should be able to do better than that. But it is a cylindrical tower over here, and they call these things the cooling towers that we are going to go and have inside here. And what you'll see, you can drive down into the state. Well, you can't right now because of COVID, but if you could drive down to the States, Washington's got a lot of these. You're going to go and see what looks like smoke coming out of those things. It's not smoke, it is just water vapor, it is steam. And what they're doing inside of these is they're creating a nuclear reaction. The nuclear reaction creates a massive amount of heat. So deep inside the bowels of the power plant, they're creating a lot of heat just from nuclear reactions. That heat is then getting stripped off continuously by water jacketing. They're superheating this water, they're running that water then through a steam turbine, and then they are cooling it down and they're trying to recirculate. Now they're going to have to lose some and they're always going to have to be replenishing, but the bulk of the water stays inside of this closed loop system where it's just going through and it's just spinning this high-speed turbine over here. Very, very common throughout other parts of the world. We just don't see a lot of them in ours, but they would be using these cylindrical alternators to go and run their steam generators. We do have cogen in BC, which does use the same process of heat, not nuclear heat, but the same process of heat with steam. You'll see a lot of this up in northern BC where you are dealing with wood, pulp and fiber, and what they're going to do is they're going to go and take any, garbage wood that gets harvested from the forest, all the bark, all that type of stuff, and they're going to go and dry it. They're going to go and run it through these massive gas-fired plants where they're going to go and use the gas to kind of get it started and keep the heat up, but they're going to be, for the most part, just be burning the waste wood from the processing of, wood for pulp and fiber and paper and, lumber, etc. They're going to burn all that. They're going to go and run it through these regen places where they're going to just create steam and they're going to burn that off. And a lot of places up in northern BC, because we have so much water, they don't operate off of a closed loop with the nuclear. They really want to because they want to try and eliminate radiation. But where we have it, in a lot of cases, they're going to be an open loop system where they're continuously pumping in water from a well or something like that, running it past the boilers, heating it up, and then sending it up the tower to go and spin these things to go and power their own sites. Relatively small compared to my salient pole, which had tons of norths and souths going all the way around. These are usually only going to go and have one or two poles, meaning it's not just going to have a single north. They mean it's going to be pole pairs that we are going to go and have. Field excitation. Let's talk about the field excitation. This is a critical part of any alternator, is having our field excited. And excitation just means we're providing some DC for our actual alternator. We've talked about this whole section just now, which is the construction of the alternator. This alternator that's shown over here could either be my cylindrical or it could be my salient. I really don't care which one, but it is going to be one of the ones that has the revolving DC field. We're just going to go and stick an arrow here on that DC field. We need to go and take that DC field and provide power in. That's going to be done through the use of our slip rings and brushes. I'll just go and draw that little symbol here for a slip ring there and a little symbol for a slip ring over here. So we're carrying the power into that field off of our slip rings and brushes from outside. We need to create this so we can create the flux so that we can go and create our value of voltage, right? We know this formula, Eg is equal to K phi n, the amount of volts that we're going to generate, whether for DC or for AC, is going to be based upon the type of machine, the constant, the flux that we are going to go have, and the rotational speed. And if I have got, flux and rotation, but no machine, or speed and a machine but no flux, etc., we would get no volts out. We need to have all three of these inside of here. What we're looking over here at is what is called a self-excited alternator and controls. Before I go into the self-excited, I'm just going to talk about what separately excited is. Separately excited would be the exact same as all of this, except I'm going to go and remove all of that over there, like so. Separately excited would be where I'm just going to go and have another DC source. We're going to stick it in as a battery here right now. But that other DC source would be brought in to go and feed this circuit. That's a separately excited alternator over there. I have something that's outside of the circuit, that's DC, that I'm using to go and control it. Ultimately, it's not very efficient because if it's a DC battery, the battery's going to deplete, so I would have to go and recharge that thing anyways and probably be recharging it off of these to go and run that. It's not going to give me, any massive benefits to go and do that because now I'm maintaining two separate systems. We like to keep everything as compact as possible. So separately excited, less common than what is going to go and be self-excited. This is the self-excited alternator over here. In the self-excited alternator, what we actually have is we have got two separate alternators. One of them is in a lot of cases going to go and be a DC generator. We're going to start with one of the DC generators, then we're going to look at one of the AC rectified ones. This one is going to go and be just a DC exciter over here. I'm going to go and have an armature inside of here, and I'm going to go and have fields around this thing, right? Same thing what we looked at before for DC. We're going to use that DC generator. We should have a small amount of residual magnetism inside here. So what's going to go and happen is that as my prime mover, which is attached to this common shaft, as my prime mover starts to go and rotate this common shaft, we should go and get this that is going to start to spin inside of that residual magnetism, which is going to generate a small amount of voltage, which is then going to get fed back into its own coil, which is going to go and increase the amount of flux, which is then going to go and allow it to increase the amount of volts, etc. And so we're going to go and have voltage buildup. That's going to go and happen on this alternator over here, this DC exciter. The DC exciter at this point, you'll note we have not connected it in to my actual main alternator that I have over here. So I'm going to get this thing up to speed. I'm going to start my main machine over here right now. The main machine, whatever it is going to be, water turbine or engine, is going to start rotating this thing together. As it rotates, we start to build values of voltage. So I'm going to just see my voltage rise across here. What I can do then is I can go and connect in across here with this specialized type of switch that's going to be called my field switch. The field switch operates in a stepped sort of manner. What it has, it's got this field discharge resistor. Now, normally, when the switch would be open like this, what I would want to have is I would want to have a complete path going across. I'm just going to go and trace through that complete path, going across through that and back up like that. Because that's going to go and prevent me from having any ridiculously high induced values of voltage. So I want this to be in there anytime that I've got this switch open like that. Which means that anytime that the switch is open, this bar is going to go across. And actually, before the switch even starts to open, it's going to make connection to that itself. So there will always be that path. As soon as my switch closes, though, when my switch closes, the action that's going to happen is first, these lines are going to go and connect across here. So they're going to connect across to this, which has got some value of voltage. Let's just call this thing 24 volts. It doesn't have to be any sort of magical number right now. It's going to have 24 volts that we're connected across. I would see that delivered right now, the instant that I'm closing in the switch right now, from my alternator. I'm just going to remove that there. I'm going to go and have current that is going to go and travel through here, through my main DC, like that. At the same time as I'm going to go and have a smaller value of current that is going to go and travel through here and through that field discharge resistor. So for just a brief second, I'm going to go and have that blue path over there. That blue path is just going to be me going through that field discharge resistor. At the same time, that's okay. This thing is going to be rated for whatever that value of volts is. But remember, we said this thing only operates like that for a split instant. As we're closing in, we've still got that little bar across it. Once we actually close in, this circuit opens over here. Okay, so now I've got my field switch that is fully closed in. That means that that little connection over there is going to be open. There's going to be no current flow through the field discharge resistor, and all the current flow is going to be through these yellowed over lines over here, meaning that my DC exciter is sending DC to my DC field over here, which is then going to allow me to go and generate AC off of here. If I want to go and open the special field switch, the first thing that happens as I'm starting to go and open it is that I'm going to go and reestablish that very first connection across the field discharge resistors. The first thing that happens as I start to open is this connection gets remade here again, which means that now I'm going to go and have current delivered from here going through there. That's going to be fine. Then as we continue to open the switch, it's going to break this contact, and as it does so, what's going to happen is this stays intact over here, and because I'm still rotating, I'm going to go and have this. That's going to be closed across here, so that any sort of residual magnetism that is, causing me to generate voltage, right? Because I've got all of those things that are going to happen inside of here, is not going to go and give me ridiculously high value of voltage. Really, we're trying to avoid inductive kick off of these ones. There's a fair bit of maintenance that's going to be involved with these when you take a look at them, because if you look at the components over here, we see that I have got slip rings and brushes on this one over here. I've got brushes and commutators. So that's 4 sets of brushes for both my slip rings and for my commutator that I'm going to have to go and maintain. I'm also going to have to go and maintain this field switch, and I'm going to have to go and maintain my field discharge resistor that I'm going to go and have over here as well. Make sure that these things don't get overheated from too long operation or anything like that. There's a better method called the brushless exciter. The brushless exciter is actually pretty freaking cool when you take a look at it. We're going to start out this thing with a little bit of residual magnetism inside of my exciter alternator. What this has is it has got a whole pile of stuff that is actually physically bonded onto the main shaft. None of these components inside of here ever leave that main shaft. They show a main shaft kind of in the background, but I'm going to have the rotor field. I'm going to have a rectifier that is going to be attached onto that shaft, and I'm going to go and have an AC rotor that is also going to go and be attached onto that same shaft over there. It's pretty cool because now I have 0 brushes. If you take a look through this, I dare you to try to find a brush inside here. There is no brushes inside here. I don't have any commutator, I don't have any slip rings, I don't have any brushes that need to be maintained inside of here. Here's what happens inside of here. We start up our prime mover, which is going to go and cause rotation on this and rotation on this, and this is just going to be diodes glued onto the shaft, epoxied onto the shaft, that are going to be spinning as well. I don't care. That's easy for us to, mount those on there. That doesn't make any difference to us. They're not doing any generation or anything like that. What happens at the instant we start turning this is there's a small amount of residual magnetism. What we have inside of here is we have got a 3-phase AC rotor. It's going to be an alternator that we are going to go and have inside here that is going to be just running off of a little bit of residual magnetism. EG is equal to BLV, or EG is equal to K phi N. Either one of those will tell you that this thing, as we rotate coils inside the flux, will generate that value of voltage. That value of voltage, as we pass it through here to that rectifier, is now going to go and get rectified. What type of rectification do we have here? Well, if we take a look at it, we see that we have got full wave rectification. There's 6 rectifiers on here, which means that my DC that's going to be coming out is going to be this, ribbly line that's going to be held well above there. It's going to be a fairly constant value of DC. Way nicer than the really humpy looking DC that we would have gotten out of this, right? This would have been just our classic half-wave rectified. This is now going to be a much more smooth type of DC that we are going to go and get out of here as we pass AC, small AC. We are then going to go and take it into DC. That DC inside of here is now going to give us that rotating field inside of our main alternator, which has got its 3 windings on it. Here, we'll just draw these 3 windings on it just as little scribbles right now. We rotate this magnetic field, which has now been powered up because we've got this DC inside here, into here, and as a result of that, these are going to go and start providing voltage, right? EG is equal to K phi N. This is going to start to generate values of voltage. And then what I'm going to do, a wonder of wonders, I am going to go and tap off of 2 lines. Doesn't matter, pick any 2 lines. I'm going to go and tap off of 2 lines in this case that I'm going to go and feed back into a bridge rectifier, and that bridge rectifier, I'm then going to go and adjust that value of DC that's going to come out with a field rheostat to adjust the value of current that I'm going to go and have transmitting through here. Remember, up until now, everything's been from the residual, giving me small voltage. We rectify that voltage. We then go and create a DC. That DC is inside of here, creates an AC. Now we're taking that AC back into a DC, and then we are going to go and send that DC through this coil over here, which is going to go and give us a lot more flux inside of here. So now we're going to fully be able to go and flux this out, which means we are going to go and generate full value of AC voltage off of that alternator, which is going to give me a higher value of DC over here, which is going to give me a full saturated field inside of this AC stator, which is going to bring me all the way up to full value of voltage on these lines on the outside. It is wonderful because we do not have any sort of brushes for us to go and maintain inside of here. It makes our life so much easier to go and deal with this. If I want to adjust the value of voltage that I'm going to go and have on my output, it's still going to be done through a field rheostat. Just my field rheostat is going to be going through a couple of steps to adjust my output value of voltage. I'm going to go and take my field rheostat. Let's say that I'm going to go and increase my value of resistance. If I increase my value of resistance, that is going to go and decrease my value of current. If I decrease my value of current, that is going to go and decrease my value of flux. That is going to be on the alternator, flux alternator, which is going to go and decrease my value of volts on the alternator as well. So the volts on the alternator are going to go down, which is going to go and decrease, because those volts go through this rectifier, decrease the amount that I'm going to go and have on this main alternator over here, the main flux over here. So flux main is going to go down. If my main flux goes down, then my EG, my total generated value of volts, is going to go down as well. So we can still do that through here. Last thing that I want to say on this one is that you can go with a single phase bridge rectifier for this one. Alternatively, we could come off of all three of these lines here as well, and we could have a three-phase rectifier system inside of here as well. We'll just scratch this whole thing over here, go to a three-phase rectifier, and then come out of that three-phase rectifier and feed that over to this circuit over here, and it would just be a more smooth DC that we would have coming out of it. You'll see either or. It's obviously cheaper for us to go and make only two connections and run stuff off of the single phase bridge rectifier, but it could be done off of alternate ones as well. Nameplate data. Over here we have got a nameplate that is, kind of a copy of what our classic man ones are going to look like. It's just going to go and tell us a little bit about it. You're going to see ratings inside of here that are not going to give you ratings inside of kilowatts. They're always going to give us inside of kVA, because we have no idea what our customer is going to go and hook up to that, or what the power factor will be. If we don't know what the power factor is, we don't know what the actual kilowatts are going to be. We always go and give everything off the kVA capabilities. That way it's up to whatever my customer does, puts into his plant. That's going to go and select the amount of VARs and the kilowatts. As long as whatever they put in for VARs and kilowatts are going to go and stay below my total kVA, this thing is going to be able to go and generate that one. Bunch of other stuff that's going to be on here. You're going to go and have volts. Usually it's going to be a slash rating if you've got multiple winding connections that you can go and make. And then phase is going to tell you three-phase. kVA for sure in there. Sometimes it's going to go and give us the watts, but it is not given for these things in every single one. Power factor is going to go and talk about the ideal power factor for it, not necessarily what you're delivering. Remember, your load is going to go and select that. Amps is going to be maximum amount of amps that we can go and have out, and then we're going to have a separate one over here that's going to be my DC. That is just going to talk about my exciter inside of there. Temperature rise and RPM is going to be based upon the electrical characteristics. We know for every 10 degrees over 30, we get 50% less life, so we want to go and keep this thing down to a relatively cool type of temperature so we can go and maintain our systems. All right, that is it for our Learning Task 1. We're going to start talking about the operating principles in our next one. Some vectors coming up.